In this video, I want to show you how we can use geometry or symmetry for evaluating double integrals. So attention, we don't want to use integral techniques for finding double integrals. We want to use properties that we know from geometry or symmetry for evaluating double integrals. Our first example is we want to find double integral of the function 3x plus 4 over region D, and the region is y is between 0 and square root of 25 minus x to the 2. The first thing that we have to do is to draw this region. But for that, let me remind you an important equation. X to the 2 plus y to the 2 equals a to the 2 is the equation of a circle that its radius is a. For example, x to the 2 plus y to the 2 equals 9 is a circle that its radius is 3. This is the thing that you need to know. Now, if you pay attention, from this equation x to the 2 plus y to the 2 equals a to the 2, if we solve this equation for y, we can write this equation in the form of y to the 2 is a to the 2 minus x to the 2. If we take a square root from both sides, y equals plus minus radical a to the 2 minus x to the 2. This is very important equation. Y equals radical a to the 2 minus x to the 2, and y equals negative radical a to the 2 minus x to the 2. The reason that we have a plus minus for the radical is that the plus sign shows the upper part of the circle. So this semicircle here is radical a to the 2 minus x to the 2, and the radius of the circle is a. The minus shows the lower part, this semicircle that is below the x-axis. This equation shows all of this circle, but when we convert this to this form, the plus sign is upper part of the circle and the minus sign shows the lower part of this circle. Now that we know these things, let's back to our question. Here, if you pay attention, y is between 0 and radical 25 minus x to the 2. Y equals, please attention, y equals radical 25 minus x to the 2 is a semicircle that its radius is 5. So here is 5, of course, and here is negative 5. So y equals radical 25 minus x to the 2 is this. The graph of this function is this. But here, y is between 0. What is y equals 0? Y equals 0 is this. Is the x-axis basically. Y is from 0 and it continues up to this curve here. Now you should be able to understand that the region is this basically. The region that we want to find the integral of the function over that region is here. So this is the region D, which is between 0, which is this line, and this semicircle. So this is our region. Now that we have the graph of the region, we can use a symmetry property for evaluating this double integral. Let me show you how we can do this. For finding double integral of the function 3x plus 4 dA, attention that we can write this double integral in the form of double integral over region D of the function 3x plus double integral of the function 4 dA over region D. Now please attention. Again, I have to remind you something that is very important. If the function f is odd with respect to variable x, a two-variable function like f of x and y is odd with respect to x if f of negative x and y equals negative f of x and y. So please attention. We say a two-variable function, whatever it is odd with respect to variable x because it has two variables. It can be odd with respect to x or it can be odd with respect to variable y. It is odd with respect to variable x if f of negative x and y equals negative of f of x and y. So what this means, here if we substitute x with negative x in the equation of the function, if we substitute x with negative x, we can pull out the negative and we can put the negative here. Let me show you an example of a two-variable function that is odd. For example, the function f of x and y equals x to the 3, y to the 2. This is odd with respect to x. The reason is that if we calculate f of negative x and y, if we substitute this x with negative x, this equals negative x to the 3, y to the 2. If we simplify this is negative x to the 3, y to the 2. What is this? This is the original function f. So this part is f of x and y, but we have a negative now here. So f of negative x and y equals negative of f of x and y. So this function is odd with respect to x. And in a similar way, we can define a function that is odd with respect to y. But what is the advantage of this? Why we need this? If a function, please attention, if a function is odd with respect to variable x, then please attention, if a function is odd with respect to variable x, then the double integral of the function f over a region D is 0 if the region D is symmetric with respect to y-axis, which is x equals 0. If the region D is symmetric with respect to x equals 0, which is y-axis. This is the thing that we want to use here. So let me review the story again. F is odd. If a function is odd with respect to x, and this is important, if the region that we want to find the double integral of the function over that region is symmetric, like this example that here we have, is symmetric with respect to x equals 0, then the double integral is 0 and we don't need to calculate the double integral. The answer of that double integral is 0. And we have a similar statement like this for the variable y. So what is the statement? If the function is odd with respect to variable instead of this y, which means that f of x and negative y equals negative f of x and y, then the double integral of the function f over a region is 0 if the region is symmetric with respect to y equal 0. So we have a similar statement for variable y. But how we want to use this for our question here? Please attention. The function 3x is odd function. It should be clear for you why this is odd. Let me name this function f of x and y equals 3x. Then f of negative x and y equals 3 times negative x, which is negative 3x. The 3x is the original function, so this equals negative of f of x and y. So f of negative x and y equals negative of f of x and y. So this function is odd. It is really clear that that function is odd with respect to x. Because the function is odd, and by looking at the region D here, we can see that this region is symmetric with respect to x equals 0. So without calculating this double integral, we can say that this is 0. But attention, for the other integral, for this integral, we don't have this claim because this function is a constant and constants are not odd because it's the same number, it doesn't change, and so the constants are not odd functions. Basically they are even functions. It doesn't matter if it's 4, 5 or whatever. As long as we have a number, the numbers are even functions. So we can use this fact, we can use this rule for this part, and we can say this integral is 0. So far we know that this integral is 0. But what about this? Here we have a 4 is a constant, and because it's a constant we can move this 4 to the outside of the double integral because it is a constant. So far we have this equals 4 double integral of 1 dA, or dA simply. This is 0. For this part we move 4 to the outside and we have this. Now the thing that you need to know here is that whenever we are finding the double integral like this from function 1, the double integral of 1 shows the area of the region. So again, let me repeat this. Whenever we are finding double integral of function 1 dA over any region, it doesn't matter what is the region, this would give you at the end the area of that region. If the region is a rectangle, this gives you area of the rectangle. If the region is triangle, it gives you the area of the triangle, whatever the region is. In this case we have a semicircle, so this gives you the area of that. So this equals 4 times area of this semicircle, that we have. And the good news is that we know the area of a circle. Just simply we have to divide it by 2. It would be the area of semicircle. So 4 times by 1/2, because it's semicircle. 1/2 the area, 1/2 of area of a circle is area of semicircle. Area of a circle with radius 5 is pi times 5 to the 2. So the answer is 4 times 1/2 is 2. 2 times 25 is 50. 50 pi. So the answer is 50 pi. So as you can see, we calculated this double integral without any integration technique. We used symmetry properties, geometric properties, and we calculated the double integral. And the answer of the double integral is 50 pi. Now look at this example. Double integral of the function x plus y over square root of 1 plus x to the 2 plus y to the 2 plus 1 dA. D is the region inside the circle x to the 2 plus y to the 2 equals 1. Let me draw the region here. It's a circle with radius 1. So this is the circle 1, 1, negative 1 here, negative 1 here, and the radius is 1. So this is the region. All of this is our region. We want to find this double integral over this region. Of course, if we want, we can try to find this double integral with the integration techniques, but probably it would be a little challenging. And one technique for finding this double integral is to use polar coordinate, transform this from Cartesian to polar coordinate and calculate this double integral in polar coordinate. But definitely using symmetry and geometry techniques is definitely better idea. Let me show you how we can do this. We can write this double integral in the form of double integral of the function x over square root of 1 plus x to the 2 plus y to the 2 plus y over. So I am dividing the terms in numerator over denominator. So basically we have same function, but I prefer to write it this way. And I have a good reason for this. Please attention. This function is odd with respect to x. So this function here is odd with respect to x. This function is odd with respect to y. Let me show you the reason. For example, why this function is odd with respect to variable y. Let me name this function f. So f is y over square root of 1 plus x to the 2 plus y to the 2. If we calculate f of x and negative y, then this function equals negative y over square root of 1 plus x to the 2 plus negative y to the 2 is again y to the 2. If you pay attention, this expression is exactly negative of the original expression, because f of x and negative y equals negative of f of x and y, so this means that this function is odd with respect to variable y. And in a similar way, you can show that this first term here is odd, this term here is odd with respect to x. If you look at this region, you can see that this region is symmetric with respect to y equals 0, and it's symmetric with respect to x equals 0. It's completely symmetric. Because the property that I explained in the previous question, so immediately we can conclude that the double integral of this part, this term, over the region D, because the region D is completely symmetric, the double integral of this is 0. So the double integral, let me separate this so to make it more clear. The double integral over region D of x over square root of 1 plus x to the 2 plus y to the 2 dA, this integral is 0. Also the double integral of the function y over square root of 1 plus x to the 2 plus y to the 2 dA over region D is also 0. This double integral is also 0. The only integral that we have to calculate is 1 dA or dA over region D. So again, this is 0, this is 0, and we know that the double integral of 1 dA is area of the region, so this equals area of this circle. What is area of a circle with radius 1? Pi times r to the 2, pi times 1 to the 2 is pi. So this double integral over this region is pi. Now look at this example. We want to find the double integral of the function square root of r to the 2 minus x to the 2 minus y to the 2 dA over region D, which is a disk. Its center is at 0, 0, and its radius is r. Here you can see this surface. Surface z equals square root of r to the 2 minus x to the 2 minus y to the 2 is the upper part of a sphere. X to the 2 plus y to the 2 plus z to the 2 equals r to the 2. You know that this shows a complete sphere. If we solve this equation for z, we get two equations, plus minus radical r to the 2 minus x to the 2 minus y to the 2. The plus is the upper part of the sphere, the minus is the lower part of the sphere. So this surface is a sphere. So basically here we want to find the volume. So what is the interpretation for this double integral? The interpretation of double integral is volume under the surface, but this surface is a sphere, half of a sphere. So this is volume under this surface. Z equals radical r to the 2 minus x to the 2 minus y to the 2. But we know that this shows upper part of a sphere with radius r, because this is r to the 2, its radius is r. And the good news is that we know the formula for volume of spheres. Volume of a sphere is 4/3 pi r to the 3, and because this is half of a sphere, so it is semi-sphere, so the area would be the area of a sphere divided by 2. Attention, this region is exactly this circle that you can see here. This is a circle, this is a disk, its center is at 0, 0, this point is 0, 0, and its radius is r. So it makes sense that this is a full circle with radius r. So we want to find all the volume that lies below sphere, this sphere, or half of a sphere, over all of these regions. So we want to find complete volume on their sphere. So without doing a calculation, any calculation, we know that this equals 1/2 of volume of a sphere. What is volume of a sphere? 1/2 times by 4/3. Volume of a sphere is 4/3 pi r to the 3. It equals 2/3 of pi r to the 3. And this is the answer of this double integral. Now look at this example. What is the double integral of the function 3 minus y2 sine of x to the 3 plus y3 e to the x dA over this region D? First, let me write this double integral in form of three integrals. Double integral of 3 dA minus double integral of the function y2 sine of x to the 3 dA plus double integral of the function y3 e to the x dA. Probably you know the reason that why I am doing this. The reason is that this is odd with respect to variable x. This is odd with respect to variable y. For example, let me tell you why this function is odd. Let me name this function f. So f is y2 sine of x to the 3. Why this function is odd with respect to variable x? Because f of negative x and y equals y2 sine of negative x to the 3. Negative x to the 3 is negative x3. So this equals y2 sine of negative x to the 3. We know that sine, tangent, cotangent, these are odd functions. Cosine is even function, but sine, tangent, and cotangent, these are odd functions. And because these are odd functions, we can move this negative to the outside. We can put this negative here. So this equals, this is a trigonometry property. This equals negative y2 sine of x to the 3. This is the original function. This is f. So this equals negative of f of x and y. So this shows that f is odd. So y2 sine of x to the 3 with respect to variable x is odd. And easily you can check that this function is odd with respect to variable y. It is very simple. Now the only thing that we have to do is to draw this region. The region is inside this equation. Absolute of x plus absolute of y equals 1, but here is less than equal 1, so inside of this equation, absolute of x plus absolute of y equals 1. Its graph is like a square that is rotated 45 degrees. This is a square, this is 90 degree, 90 degree, 90 degree, 90 degree. Here is 1, 1, negative 1, negative 1. This should be here. Okay. Hopefully you understand that this is a square that is rotated 45 degree. The reason that this is a square is that these are all the same and these angles are 90 degree. As you can see, this region, this is the region inside of the square because it is less than equal. This region is symmetric with respect to y-axis, it's symmetric with respect to x-axis, it is symmetric with respect to x equals 0, it is symmetric with respect to y equals 0. Because of this, because of symmetry of the region, this integral is 0. This integral is also 0. So the only thing that we have to do is to find the double integral of 3 dA. For this, we can move the 3 to the outside, so we have 3 double integral of dA over region D. And we know that this is the area of a square. What is the area of a square? We have to find the length of one side, and we have to square that. If this side is, for example, 5, 5 squared is 25. But what is the length of this? Attention, this is 1. And this is also 1. If we use Pythagorean theorem, simply we can find the length of this, and the length of this would be radical 2. So the area of the square is 3 times radical 2 to the 2. Radical 2 to the 2 is 2. 2 times 3 is 6. So this double integral over this region is 6. The other thing that I have to mention is that if you want, for example, to find the double integral of the function y to sine of x to the 3 over this region, you cannot find this with the integration techniques, because sine of x to the 3, for finding the integral of this part with respect to x, you cannot find this because we don't have any formula or any method for finding the integral of sine of x to the 3. And we cannot find its integral based on elementary functions. We cannot write it in finite terms. So this is the only way for finding the double integral of this term over this region. You have to use property. You don't have any other choice. I hope by watching this video you have learned how we can use geometric properties, symmetric properties for evaluating double integrals over general regions. If you liked this video, please subscribe to my channel and see you in the next videos.